So welcome to lesson number 2, reflection 1 from the light and sound section. And this lesson is lesson 2, part 2, where we're going to look at reflection of plane surfaces. Plane, in this case, meaning flat surfaces. So make sure you have your notes downloaded so you can work along with me. So I'm going to the section on reflection of plane surfaces. Now, we're going to talk about light, and we're going to talk about light being a form of energy which travels in straight lines, and we'll call these straight lines rays of light. Now, 3 things can happen to light when it falls on a surface. It can be reflected, it can be transmitted, it can be absorbed, or combinations of all 3. So let me look at that in a little bit more detail. So, reflection of plane surfaces. Well, let's start off with a mirror. I'll explain a little bit more detail about a mirror in a few minutes. Let's say I've got a ray of light that is incident on a mirror. So I'll represent my ray of light just as a straight line, as such. And what happens to that ray of light? Well, that ray of light, we've already talked about reflection of waves in the previous part of a lesson. That will be reflected like this. The angle of incidence is equal to the angle of reflection. So, in the case of a mirror, that ray of light will be reflected. So, mirrors are very good reflectors. What about clear glass? So what happens if I shine light onto clear glass? Well, the light goes through the glass. We say it is transmitted. You might also see a reflection in glass as well. So there could also be some partial reflection. So you can get combinations of these occurring. But by and large, light shone on glass will pass through. So that ray of light will be transmitted. And what happens if I shine light onto something like a blackboard? So here's my incident ray coming in. Well, black is something that absorbs the light. That's why it is black. More about that later when we do colors. But that incident wave just gets absorbed by the black surface. So the ray of light is absorbed. Now, no surface is a perfect reflector, a perfect transmitter, perfect at absorbing. So you usually get combinations of all 3. But primarily, a mirror is a reflector, glass is a transmitter, and a blackboard will absorb. Let's talk about plane mirrors. The word plane is going to mean a flat mirror. In the next lesson, we'll be looking at curved mirrors. So we're talking about flat surfaces. So how am I going to represent a mirror? Well, that line there represents the surface of the mirror. I'm going to shade the back of it. This is the back of the mirror that doesn't reflect. So the reflecting part is above the mirror, and the back of the mirror is the non-reflecting part. So if I shine a ray of light onto that mirror, you're going to shine it from this side. I'll just represent it by a ray. So once again, you know what that is. That there is the incident wave, or here we just might call it the incident ray. You measure angles, of course, with respect to a line perpendicular to the mirror, and that line is called a normal. And the incident ray makes an angle of incidence I to the normal. And then what happens? Well, the incident ray gets reflected, So we get a reflected ray at the same angle as the angle of incidence. So this here is your angle of reflection. Here's your reflected ray. And once again, the law of reflection will hold, of course. The angle of incidence, I, is equal to the angle of reflection, or. So we're doing the same thing as before, except we're primarily concerned with light. Let's have a look at how images are formed in plane mirrors. So here's my mirror. There's the reflecting part on this side, and there's the back of the mirror. And I'm going to take an object. I'm going to call objects by the letter O. And I want to find out where its image is formed. So I'm going to represent the images by the letter I. Now, if I take that particular object there, well, there's an infinite number of rays of light coming from it, getting reflected from other materials or whatever. But there's an infinite number of rays coming from that. I'm just going to take 2 rays and find out where they end up. Any 2 rays whatsoever. So let's take a random ray of light coming from this particular object going towards the mirror. Well, what happens to it? Well, it's going to obey the laws of reflection. So the angle of incidence is equal to the angle of reflection. So that ray of light will bounce out at the same angle it came in. And of course, it obeys the laws of reflection. So if I put my normal in there, N, and the angle of incidence I is equal to the angle of reflection. Right, let me take another ray of light. Any ray of light whatsoever. Let's say I take, for example, this ray of light here. So it goes from the object towards the mirror. Then it hits the mirror. It's going to bounce off the mirror at the same angle it came in. Once again, the angle of incidence is equal to the angle of reflection, but I won't bother putting all that in again. Now, there's 2 of an infinite number of rays. Now you're looking into the mirror. Let's say this is your eye here. So I'll represent an eye in physics like this. So there's your eye. You see these rays of light getting reflected off the mirror? There's one, there's another. They are diverging. They are getting further apart. They will never come together to form an image. So what happens in your mind's eye? In your mind's eye, you will work them back to where you think they're going to meet. So I'm going to work them back to where I think they're going to meet. So take that ray on the right-hand side. I work it back. Take this ray here on the left-hand side. In my mind's eye, I'm working it back. And those 2 reflected rays appear to meet here behind the mirror. So that's where I think the image I is being formed. If you can do as many rays as you want. They will all work back to that point I. Now, those rays of light only appear to meet. And because they only appear to meet, that kind of image that's formed, that image is what we call a virtual image, where the rays of light only appear to meet. That is the first property of an image in a plane mirror. It is virtual. A real image is where the rays of light actually do meet. And you'll see that in the next lesson when we look at curved mirrors. Let's just go back to my notes for a second. Here are some definitions that you need to learn. We've just talked about the virtual image. So a virtual image is one in which the rays of light only appear to meet. It cannot be produced on a screen. Whereas a real image, that's one in which the rays of light do actually meet, and you can produce it on a screen. So the virtual image is formed inside your head. The real image can actually be formed on the screen. But we'll see real images in the next lesson when we do curved mirrors. Now we're looking at the properties of images in plane mirrors. The properties are sometimes called the nature of an image. And the first part of the nature is the image is virtual. The second part of its nature, number 2, just if I go back to my diagram here, you see where that image is? If I draw a line from O to I, and of course, this part of the line here represents the normal. You could actually prove this very simply using geometry, that the distance ON is equal to the distance NI. And do you know what that means? It means the image is as far behind the mirror as the object is in front of it. That kind of makes sense, doesn't it? You know, when you're looking at your image inside a mirror, the more you walk back, the more you can see your image going back into the mirror. So the image is as far behind as the object is in front. So looking at your notes, you can see the second part of the nature, the image is as far behind as the object is in front. ON is equal to IN in your diagram. There's one more property. You might have thought about it. You might know this already. When you try to read from a mirror, the writing gets laterally inverted. So my third property of an image in a plane mirror is lateral inversion. When you look at writing in the mirror, the writing doesn't go upside down, but it gets sideways turned around. That's called lateral inversion. For example, if you look at the letter E, and you look at that in a mirror, the E appears like that. It's not upside down, but it's sideways turned around. You might see the word ambulance on the front of an ambulance. That's written sideways inverted. That's not because somebody made a mess of it. It's when you look at the word ambulance in your rear view mirror, it appears the right way around. Let me explain where this lateral inversion thing comes from. There's my mirror again, reflecting part back at the mirror. Let's say I've got an object. We can represent the object in any way we want. In the previous part, I represented just as a dot, but often we represent objects as arrows. So let me say I've got an arrow here, and there's my arrow. I'll say that point A is on the left and point B is on the right. Let's say you look at this arrow. So here's my eye here, and I'm looking at that arrow. Well, when I look at that arrow, I can see that A is to the left of B. A is left of B. Now I want to look at that, the image of that arrow in the mirror. Well, I've already said this, haven't I? Where does A appear in the mirror? Well, A is going to be as far behind the mirror as the object is in front of it. So there's the image of A. I'll call that A dash. And what about B? Well, B will be as far behind the mirror as it is in front of the mirror. So if I work back here, here's the image of B, which I'll call B dash. And now my arrow, this is the image of the arrow in the mirror if I join A dash to B dash. Now let me turn my eye around. So now I'm looking at the image in the mirror. And when I look at that now, when I looked at the original object, which we call O, and the image which we call I, when I looked at that, A is to the left of B. But now when I look into the mirror, I'm going to see that A dash is right of B dash. In other words, it's been sideways turned around. It's been laterally inverted. Let's have a look at example 2. Two mirrors make an angle of 120 degrees with each other. A ray is incident on mirror A. Let's have a look at example 2 from your notes. We've got two mirrors. They make an angle of 120 degrees with each other. A ray is incident on mirror A at an angle of 55 degrees to the normal. Find the angle of reflection after it's reflected from mirror B. So I've redrawn it here. So first of all, we are told that the angle between the mirrors is 120 degrees. We're also told that the angle of incidence of the ray coming in and hitting A is 55 degrees. Well, you know, don't you, that the angle of incidence is equal to the angle of reflection. So this angle here is 55 degrees. Now you're just going to do a simple piece of geometry. You're just going to go around all the angles and the triangles. That line is a normal N, which is perpendicular to the surface. So if that's 55 degrees, take it away from 90. This angle down here is 35 degrees. Next, I'm going to move on. I've got a triangle here. The three angles of a triangle add up to 180 degrees. So this final angle in the triangle, that will be 25 degrees. Once again, we're over to the normal, which makes a 90-degree angle with the surface. If that's 25 degrees, 90 minus 25, that will give me 65 degrees. So the angle of incidence on mirror B is 65 degrees. And now you're using your simple law that the angle of incidence is equal to the angle of reflection. So this angle here has to be 65 degrees. So therefore my answer is, what is the angle of reflection after it's reflected from mirror B? The answer will be 65 degrees. Okay, just one more thing to finish with. We have this demonstration of reflection. Now, these demonstration experiments, they're throughout your notes. And the important thing is when you answer any question, when they say, outline a demonstration experiment to show reflection, then there are three parts you should always include. The apparatus. The apparatus here is a laser and mirror. I would always have a diagram, a simple diagram along with the apparatus. The method, no need to go 1, 2, 3, 4, anything like that. Just a simple sentence or two sentences. Point the laser at the mirror. And then you want an observation, maybe a conclusion. And what we're saying here is the reflected ray bounces back at the same angle to the normal as the incident ray. That's a very simple demonstration of reflection. Okay, that's the end of this part of this particular lesson.